In this video, we're going to have a look at the basics of vectors. And to do this, we're going to revisit the scenario of the brave duckling. That duckling swam 5 metres on a bearing of 50 degrees and 7 metres on a bearing of 170 degrees. So if we revisit what that looked like, we can very quickly draw that in. Let's put some arrows to show those vectors. And we can see that we've got that resultant vector showing the displacement of the duckling from its mum. The question is, would we have the same result, the same resultant vector in green, if the duckling swam 7 metres on a bearing of 170 degrees first and then 5 metres on a bearing of 50 degrees? So if we actually consider this back to the mother duck, and having the duckling swimming on a bearing of 170 for 7 metres, so we've got a little 10 degrees in there, and then taking its 50 degrees on a bearing of 5 metres, in actual fact, yes, we would have exactly the same result, the resulting vector R being that displacement of the duckling from the mum. So this is what we have a look at when we're dealing with adding vectors one onto the other, drawing them nose to tail. And we can use what we call the parallelogram rule to represent this. So if we've got a vector A and a vector B, and we add them vector A first and vector B, we'll get this resultant vector here, but instead of calling it R, we can call it A plus B. But we've just found, just by drawing that again, if we do vector B first and then vector A, we get exactly the same result. We get B plus A. So it's showing us that vectors that occur simultaneously or sequentially, it doesn't actually matter which way we add them first. As long as we draw them nose to tail, we'll have the same result. Now it's called the parallelogram rule because, as we know, a parallelogram has opposite sides equal. So we can see that these opposite sides that are, for example, vector B, are in the same direction and they have the same magnitude. They're parallel vectors. And we also know that the triangle inequality applies here. And that triangle inequality is just using the idea of the triangle, saying that the result A plus B would be less than or equal to adding A and B separately. So the magnitude of A and B will always be less than or equal to the magnitude of A plus the magnitude of B separately. So let's draw a little bit of a summary of this. If we had vector A and then vector B, or we had vector B and then followed by vector A, we would still get the same resulting vector of A plus B or B plus A, and they are equal. So what happens when we subtract vectors? So we're going to try and look at a vector A take vector B. So let's use the same idea of vector A being the 5 metres on 50 degree angle, and then vector B being the 7 metres on 170 degrees. So if we actually draw this in, what we've got here is still considering it as an addition, but we're going to do A, vector A, so I'm going to draw that in, and we're going to add on negative vector B. So what we're actually doing with negative vector B is a vector with the same magnitude, so it's still going to be 7 meters, but it's going to go in the opposite direction it normally would. So instead of from here going in a direction of 170 degrees, it's going to go in the opposite direction. So that's going to be our vector B. So let's put a little negative on that. So again, the result would be this vector A take B, or A plus negative B. Now, could we do this the other way and say, well, let's start with negative B and plus A. So we go back to our starting point. If we did negative B and then vector A, indeed we would still have the same resulting vector. So it's telling us that A take B is equivalent to negative B plus A. So we can change the order that they're written in. And as you can see, we've got that parallelogram rule happening again. So let's have a look at a couple of examples here. I've got a vector AB and a vector BC, and I'm going to write them in that order because that's the way that the arrow is facing for the direction of the vector. So here the resultant, which would be AC, is because I've travelled up vector AB, so I'm going to write that AB with an arrow, and then I've added on vector BC, and that's given me the result of AC. And again, we can write the magnitude of AC with the lines around it. In our second example, I've just used a letter to represent the vector. So I've got vector X and vector Y. So again, in the same direction. So the result here, I'm going to call it Z. And I can say that vector X plus vector Y is equal to vector Z. So what happens when we have a vector that we're adding on, and we've got vector A plus the negative of vector A? So that's the same magnitude but in the opposite direction. Well, we know if we have vector A going in this direction and negative A would be going in the opposite direction, what we end up with is what we call a zero vector. So I've written a 0 with a little tilde or line underneath it to show that this is actually has 0 magnitude. So it's actually called a 0 vector, and it has an undefined direction. Now, equal vectors, for example, vector A equaling vector C, means that we've got vector A and we've got a vector C that are exactly the same. They have the same magnitude, so the same size, and they have exactly the same direction. But what we could do is taking vector A is we could put it what we call a scalar multiple. So remember we talked about scalar in our previous video very briefly, saying that this is just a measure of size. So when we put a scalar multiple on, and in our example here we've used K, what this does is it just changes the size of vector A. So if this was initially vector A and we put K times vector A, meaning K is 2, then we would have now 2A. Again, if we had a multiple of 3, we would have 3 lots of vector A joined onto each other. That's the scalar multiple of a vector. Now, earlier using our parallelogram rule to show that it didn't matter what order we added the vectors in, we saw that parallelogram rule with the parallel sides. So when 2 vectors are parallel is if one is a scalar multiple, which is the K we've seen earlier, of the other. So for example, if we had A, vector A, and we had another vector, let's call it vector B, which was worth 2 lots of vector A, then we would call these like parallel vectors. And they're like parallel vectors because they are in the same direction, and then B is just some scalar multiple of A. So if we had now vector C, that, for example, may have been negative 2 lots of vector A, what this means is they are unlike parallel vectors. And what makes them unlike is that they are in opposite directions. So now we're going to take a look at a couple of examples, and perhaps you would like to pause the video and then and have a go at these yourself now to see if you can draw a diagram to represent them and do some calculations to work them out. So in example 1, to write a vector equation, what we're really looking for is where the noses of our vectors meet to see if we can work out which one is that resultant vector. So here I can see that the nose of vector C and B are meeting, and to have a go at finding, for example, vector C, I would have to do vector A plus vector B. So it's just tracing it and working out that resultant vector. So because they're placed nose to tail, I would say A plus B is equal to vector C. Again, in part B, we've got 2 noses, the arrows joining here. So I can see if I had a resultant of vector B, I would do vector C plus vector A to give me vector B. In example 2, we have vector A with a magnitude of 7 in the direction of 120 and B a magnitude of 5 in the direction of 280 degrees. So again, find the magnitude and direction. Step 1 is always to write up your diagram with the details on that. So when we do that, we're going to have vector A going off in 120 degrees. And then we're going to have a nice direction on that. And then we're going to draw in vector B, which is on a direction of 280 degrees with a magnitude of 5. So we've got a little 10 degrees in there. And now that we follow the direction of these from the starting point, nose to tail, I'm going to have my result here in green, and that's going to be vector A plus vector B. So using what I know about the angles, I can work out that I've got an angle of 20 degrees in here opposite the resultant vector, and I can use the cosine rule to work out the magnitude is 2.87 units, so 2 decimal places, and using the cosine rule to work out that angle theta of being 36.6 degrees. So it's travelling on 2.87 units on a bearing of 157 degrees. So we'll say this is about 37 degrees. Having a look at A take B, so this one will be slightly different. I'm going to think of this as A plus negative B. So I'm going to choose a starting point, and I'm going to still draw in my vector A at 120 degrees. So I've got my 7 units at 120. But from there, instead of going 280 degrees, I know it's going to go 10 degrees lower, and I've got B again coming off there for 5 degrees. So it's very, very close that resultant vector is going to come straight down here, and then I can work out that resulting vector A take B, because I've got my vector A and then my vector negative B. So using all the information that I have, I can work out that just in this part here, I've got a 160-degree angle. Using my cosine rule, I can work out the magnitude is 11.82 units to 2 decimal places. I'm going to work out this angle in here. I'm going to call that theta, and that's going to be 8.32 degrees. And it's going to travel 11.82 units on a bearing of 128 degrees, because we'll call that about 8 degrees. Final example, we've got a triangle ABC. So we need to draw this. We've got A and C. It's going to be represented by B. We've got AB and we've got CB. So we've got a direction here, and that's going to be represented by vector A. D is a midpoint on, not a midpoint, but a point on AB such that we've got a ratio of 1 to 2. So we've got D. Okay. Now we need to express the following vectors in terms of vector A and vector B. So we have a look, we want to travel from A to B. So we're going in this direction. So we're going to travel along vector B and along vector A in their directions. So AB is going to be worth B plus A. In our second example here, we've got A to D. So just that one part of those 3 parts. So it's actually worth a third of the vector AB we've just defined. So it's going to be worth a third of B plus A. And in our last part, we've got C to D. So what we want to do is travel from C to D in that direction. So let's start from point C. We're going to have to travel back to A. So that's going to be the negative of AC, because we're traveling in the opposite direction, which is going to be negative B. And then we want to travel up AD. Now we've already defined AD. So let's just put these arrows on. And AD is a third of B plus A. So if we simplify this down, C to D would represent negative B plus a third B plus a third A. So it would be a third A take 2/3 of B.